All right, video 12 will be some example problems on motion in 2 dimensions. Okay, this is going to include some problems where you are finding the components of a known vector, the Cartesian components of a known vector. And there will also be some problems with vector addition, a little bit more difficult than the one-dimensional ones that we've done so far. Let's start by going back to this problem with the rowboat in the river. We now have 2 questions added to it about this problem, besides just what is the total speed of the rowboat in the river's current. So we know that the v total is 5 meters per second, and we know that the direction is given by that angle theta there. We're being asked find theta to describe the direction the boat moves, and if the river is 36.0 meters across, when will the boat reach the shore? Neglect the size of the boat. All right, the first thing I want to point out is they're asking me the angle that it's going, and sometimes they don't give me which angle is theta, in which case I get to pick an angle and solve for that. This is not the angle I would have picked. If I had had the opportunity, I would have picked an angle inside the triangle. Giving you the angle on the outside of the triangle is a little bit tricky, but we're not going to get tricked. What I'm going to do is I'm going to complete this triangle around the theta. The dotted lines that I've drawn in here, this one represents the speed of the boat, or the velocity of the boat across the river. It was over here, and I've drawn it over here, but notice it means the same thing. It's the same length vector, pointed in the same direction, and so there's nothing wrong with moving it from one place to another like this. You're allowed to move a vector from one place to another. You're not allowed to change the size of it, and you're not allowed to spin it around to point a different direction. So similarly, I have the vector that represents the river is now represented by this dotted line down here. I probably should have chosen arrowheads for each of those two. That's okay. So that angle theta I'm supposed to try to find, I need to find a way to do some inverse trigonometry on it. And if you don't remember doing that anytime recently, here's what I'm trying to do is I want to say I need to either say sine theta or cosine theta or tangent theta equals something I already know. If that's true, I can then do an inverse function and get the theta from it. So for example, tangent theta equals opposite over adjacent by definition. And in this case, for the theta they gave me, the opposite is the velocity of the boat, right here. And the adjacent is the velocity of the river, right here. And I know the numbers for those. So that means tangent theta equals 3 meters per second over 4 meters per second, which is 0.75. So tangent of some angle theta equals 0.75. Back in the old days, when I was in high school, that meant you got out your trig table and you found by hand what angle it was that is 0.75. It was horrible. It wasn't that bad, I guess. But what you want to do instead is you want to take your calculator and you want to say inverse tangent, which is usually second button and then the tangent button. Inverse tangent 0.75. It'll often put parentheses around it, which I have neglected to do here. And then you just hit enter, and it will tell you what angle out there gives you a tangent of 0.75. That angle is 37 degrees. If you're not familiar with this, or if you don't remember having done this anytime recently, you may want to do a little bit more follow up on how to do inverse trigonometric functions. Part B, it asks me if the river is 36 meters across, when will the boat reach the shore? We're going to get a little bit more detail into this for the video on Friday, but the important point of this is this part of the velocity, the rowing, is the part that's taking him across the shore. If he doesn't row, the river current takes him downstream. The rowing is what takes him across. So believe it or not, that's the only velocity you have to worry about for this problem. As long as this rower keeps pointing the boat directly across the river like that, you can just say I'm going to worry about the velocity in the y direction. That's what's going to give me a displacement in the y direction over a change in time. So I rearrange that to say delta t equals delta y over v y average, the velocity in the y direction. The velocity in the y direction is 3 meters per second, so I can take that 36 meters divided by 3 seconds, and I get that it'll take 12 seconds to get across this river. Here's another example problem. You walk 44.0 meters due south, then 28.5 meters due west. Determine your final displacement. As anyone who has been to the WebEx sessions would know, the first thing I want to do is at least a little bit of a sketch of what's going on here. So I'm going to draw a vector that represents 44 meters due south. And then I'm going to draw another vector that represents 28.5 meters due west. It should be to scale, but to me, to scale means smaller. And that'll be close enough for now. We don't need to get out the rulers. Determine your final displacement means, well, you started up here and you finished over here, so you need a straight line vector that represents that. That red arrow is your final displacement. And now that I've sketched it, I see that that final displacement is a hypotenuse of a right triangle. I'm going to label the angle inside, theta, and I'm going to do some calculations to find the magnitude of the hypotenuse and the magnitude of the angle. So the final displacement I can find with the Pythagorean theorem. So the final displacement squared equals the y component squared plus the x component squared. So final displacement is the square root of 44 meters squared plus 28.5 meters squared, and I get that that comes out to 52.5 meters. That's the magnitude of that red vector. For the angle, I need to do the inverse trigonometry again. So I know tangent theta is a way to relate the opposite and adjacent sides, and I already knew the opposite and adjacent sides. I could use sine or cosine now that I have the hypotenuse. That would be fine also. Tangent theta is the opposite side, which is 28.5 meters to the west, divided by the adjacent side, which is 44.0 meters to south. And so 28.5 divided by 44 is 0.6477272727, etc. So inverse tangent of 0.6477272727 will give me the angle, and it's 32.9 degrees. This brings me to an excellent point, which is that there will be rounding errors depending on which calculator you're using and where you're choosing to make things rounded off, and there will be some flexibility with that. Expert TA offers you some flexibility. I will also offer you flexibility with that, especially you need to know on the test. I know your stress levels tend to go up when you're talking about the test versus the homework, especially if you're showing me your work. Rounding errors won't be an issue. So here's how we communicate our answer then. The final displacement is 52.5 meters at 32.9 degrees west of south. I want to emphasize that if you weren't sure how to say west of south versus south of west or something like that, the fact that you've said theta is 32.9 degrees and your drawing clearly shows that this is theta, to me that is a good communication that you understood this, and I would give you full credit for that, even if you hadn't included west of south as part of it here. Okay, here's another example. This one has a lot going on. This is the most complex one. So, determine the total displacement of a person who walks the following 3 paths on a flat field. First, they walk 25 meters in a direction 49 degrees north of east. That's vector A here. Second, they walk 23 meters heading 15 degrees north of east. That's vector B here. Third, they walk 32 meters in a direction 68 degrees south of east. That's vector C. And so they want to know the total displacement from the origin to where they wound up at the very, very end. Okay, I want to point out these vectors are not in the same dimension. They're not all in the x, so you can't just add them together. They're not all in the y, so you can't just add them together. They're also not perpendicular, so you can't just Pythagorean theorem your way out of this. This is much more complex. In order to add these together, what we're going to have to do is determine what the x component and y component is for each of these 3 vectors, and then we add up everything in the x direction to get a single net displacement in the x direction. we add up everything in the y direction to get a single net displacement for everything in the y direction. A single sum displacement in the x and in the y can then be expressed as Cartesian coordinates with unit vectors, or it can be converted to polar coordinates. So let me walk through how to do that. The first thing I'm going to do is take vector A, and I'm going to say it has a y and it has an x component. X and y by definition are perpendicular to one another, and the value for vector A was given, so I can, from that, the angle and the hypotenuse given to me, I can find what the x and y are. Vector A's x component will be equal to vector A times cosine theta, where I have the little subscript A next to the theta because we do have three different vectors with three different thetas. So this was theta A. And I've included an x hat here to emphasize the A component will be in the x direction. I'm sorry, the x component of A will be in the x direction. A's x component, vector A's x component will be 25 meters times cosine 49 degrees, x hat. So A sub x is 16.4 meters, x hat. What that means is vector A extends 16.4 meters in the x direction. That's what this component of A is right here. I'm going to do the same thing in the y direction. A subscript y equals A times sine theta A, y hat. A in the x direction, oops, that should say y direction, is then equal to 25.0 meters sine 49 degrees, y hat. And so A in the y direction is 18.9 meters, y hat. There, I fixed my x's and y's. Okay. So those are the two components of vector A. I'm going to do the exact same process for vector B. So let me make my dotted lines here to show the y and x components of vector B. These do not get drawn back to the origin of A. These get drawn back to the origin of vector B. B in the x direction is B times cosine theta B, x hat. B in the x direction is therefore 23 meters times the cosine of 15 degrees, which is 22.2 meters, x hat. And so every time I'm saying x hat or y hat, that just means in the x direction or in the y direction. B subscript y is B times sine theta B, y hat. So 23.0 meters times sine of 15 degrees, and I get that the y component of B is 6.0 meters in the y direction. I need to now do the last vector, vector C, the exact same thing. Notice though, vector C continues moving in the positive x direction, and then it moves in the negative y direction. So we'll see that taken care of as part of our math here. C in the x direction is the magnitude of vector C times cosine of theta C, x hat. That's 32 meters times cosine of negative 68 degrees. The fact that it's negative 68 degrees will account for this. So if you leave the negative off when you put that in there, in this case, it would still give you 12 meters and you would be okay. Where it would be a problem would be when you are going to do the sine. C in the y direction is C times sine theta, so 32.0 meters times sine of negative 68.0 degrees, y hat, and the sine function will give you a different value for positive 68 degrees than for negative. So you do want to be careful about your negatives when it comes to this trigonometric functions to break down a vector like this. All right, that's a lot of, it's not hard math, but it's a lot of it. We did the one process 6 times to find the x component and y component for each of the 3 vectors. What I now want to do with that is collect those all in one place. I have a column of all the x hats, and I have a column of all the y hats. If I take each of these x hat amounts that I calculated and add them together, I will get how far the total is in the x direction. The components of vector A, vector B, and vector c in the x direction add up to how far our total displacement needs to be in the x direction. And the same thing with the y. We're going to add this positive y value here, this positive y value here, with this negative y value here. And so we get our total values are that our resultant vector is going to be a displacement of 50.6 meters in the positive x direction and 4.8 meters in the negative y direction. I can write it like this. Total displacement is 50.6 meters x hat minus 4.8 meters y hat. That's a valid way to answer the question unless the question says specifically that we want to know the magnitude and direction of a single resultant vector for this question. In which case, I have my x and y components of that vector, the 50.6 meters in the x direction and the 4.8 meters in the negative y direction, and I would need to find the magnitude of the single long purple arrow that I have on there and the angle that it makes with the axis. So the total displacement is represented by vector d. As it says here, it's 50.6 meters in the positive x, 4.8 meters in the negative y. So with the Pythagorean theorem, I can say that the x component squared plus the y component squared gives me the magnitude of this single vector that is the hypotenuse of the resultant. And so d is a vector that is 50.8 meters. The direction of d is it's some angle theta a little bit below the x-axis, and I can find out what that angle theta is because I know the side adjacent to it is 50.6 meters and the side opposite it is 4.8 meters in a negative y direction. So the inverse tangent of negative 4.8 over 50.6 gives me negative 5.4 degrees. That's what this little angle is right in here. Or you could say that's 354.6 degrees around counterclockwise, which is the convention that mathematicians use. Meaning my final answer here was total displacement is 50.6 meters x hat minus 4.8 meters y hat. Another way of saying it is 50.8 meters at an angle of 354.6 degrees or at an angle of negative 5.4 degrees from the positive x-axis. Those are equivalent correct answers. Sometimes you are specifically told which version of or which format to use, and when you're not, then you pick whichever format seems best to you. I do want to point out your textbook goes over this problem, so if you want to see it gone through again, you can do that. They get the same answer to within some rounding errors on their part, and they also use a procedure, like I said, that engineers tend to do that we're not going to do, where they're using a ruler to sketch these all out to scale with one another. They also make an argument that it doesn't matter what order you add the vectors together. You could do c plus a plus b and get the same resultant, which is what you're seeing here. That's the associative property. I'd also like to recommend that you check out OpenStax Chapter 3 for some example problems. Example 3.3 is a really good example problem to check out. And Section 3.3, at the very bottom of it, there's a link to a University of Colorado PHYS exploration to play around a little bit and learn about vectors a little bit more. The only topic for Friday's videos will be projectile motion, which is free fall physics, but occurring in 2 dimensions.